Okay, so we are continuing with this example. Suppose we are given this word institute and we are to find the number of ways of arranging the letters of this word. Now you can see how many characters are here. I mean, without counting the number of repeated letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means we have 9 factorial ways of arranging the letters without considering repeated letters. But letters have been repeated. I appears 2 times. So we are dividing by 2 factorial. But still we have more repeated letters. T appears 3 times. So we multiply this 2 factorial by 3 factorial. So in this many ways we can arrange the letters of the word institute. Okay, let's take another one. Allahabad. For this word also, if we try to find the number of ways of arranging the letters, then it will be, first of all, you count the number of letters 1, 2, 3, 4, 5, 6, 7, 8, 9. Same 9 letters. So 9 factorial divided by, now you see how many times each letter is written or each letter appears. First of all, we have A appearing 3 times. 4 times. So we divide by 4 factorial. H, B and D each appears only once, but L appears twice. So we multiply this 4 factorial by 2 factorial. So in these many ways we can arrange the letters of the word Allahabad. By the way, in the previous one, the rest of the letters that we have not talked about, they are not repeated. For example, N is not repeated, S is also, it appears once, and so are U and E. So that's why nothing else appears in the denominator. Although you can say that since N appears once, I can write 1 factorial, but that does not make any difference and it's needless complexity. So in this way we can count the number of arrangements when objects are repeated. Okay, so now let us move on to some questions. Now the questions are not necessarily dealing with only the cases where letters are being, objects are being repeated, but there may or may not be repetitions. Okay, now let us take down the first one with no repetition allowed. With no repetition allowed. Oh, no repetition of what that I have to mention. No repetition of digits. Is, I should not write is, with no repetition of digits. How many 4-digit numbers? How many 4-digit numbers can be formed using these digits up to 9. Okay, so this is the question. It asks us to find out the number of 4-digit numbers that can be formed where the digits are not repeated and we have the digits given to us you can see that 0 is not there, right? So 4-digit numbers means we can directly, either we can proceed in two different ways for the solution. Either we can use the formula for calculating the number of permutations, or we can use the usual counting principle that we by now we are very familiar with. So let us use the counting principle first. So there are 4 places where we can put these digits: units place, tens place, hundreds place, thousands place. Okay, so here we can put any of these 9 digits in 9 ways. Now since repetition is not allowed, this place can have 8 ways of filling it up. For the third place we have 7 ways, and for the fourth place we have 6 ways. So the number of 4-digit numbers is 9 times 8 times 7 times 6, which is something. You can do the multiplication, it does not matter, you can find out the answer. What matters is the method. In the second method, you can directly find this out. You are actually trying to find out the number of permutations of 9 objects when 4 are taken at a time. Okay, and also note that the objects are distinct. It's not a situation like this where objects are being repeated. If objects are being repeated, this formula cannot be used. 9p4. This is only for distinct objects. Keep that in mind. Now we already know the expression for this: 9 factorial divided by 9 minus 4 factorial. Now this is 9 factorial divided by 5 factorial, which is nothing but 9 times 8 times 7 times 6 times 5 factorial actually, divided by 5 factorial. Why? Because if we write this product out completely, then we would write 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That 5 times 4 times 3 times 2 times 1 is nothing but 5 factorial. So these two cancel out and we are left with this. Okay, so that is the solution. So let us now take the next problem. Now the next problem also uses permutations, but I have decided to phrase it somewhat differently. We'll see why. Find the cardinality of the following set. There is a set. It is the set of all natural numbers such that n lies between 100 and 1000, and n has distinct digits. Okay, so this is the set. Now, what we have been asked here, we have to find out the cardinality of this set, that is the number of elements in S. In calculating this number of elements, actually we need to find permutations. Why? That will be clear when we write the solution. You see, look at the elements of S. They are nothing but natural numbers. Okay. Now, natural numbers, that do not all natural numbers, they are restricted using these two conditions. The first one is that the numbers we are considering should lie between 100 and 1000. So these inequalities give me this range 101, 102, etc. up to 999. Okay, but further we are restricting this list. The numbers we are considering must have distinct digits. Okay, so for example, this is not in S. This is not in S. This will be in S. Okay, this will be in S. This is also not in S. That's because here the digits are not distinct. 1 is appearing twice. Here 9 is appearing 3 times. So the digits must be distinct. Another example can be 456. This is in S. Or 798. These are numbers in S. Now at once, right off the bat, we can see that we already have the number of digits, number of numbers is one thing. In S we have the elements are numbers. We need to count the number of such numbers. That is one thing. But in each number there are 3 digits. That is important because we want to be able to use this counting principle. So we know that there are 3 digits. And the digits, unlike the previous exercise or the previous problem, now the digits are these. Because in the previous problem, it was given that the digits are to be from 1 through 9. But now 0 is also allowed because that is also a digit. Since we are using decimal number system, decimal representation of numbers, there are 10 characters. If we used binary system, there would be only 2 characters, 0 and 1. But we will discuss that thing, that is an entirely different thing. The point here is that now 0 is also allowed. And this creates some complexity that was not there in the previous problem. What complexity? You see, now for me, you may think that since 10 characters are available, just like we had 9 characters available in the previous problem, now this place will have 10 choices. But that is not true. It's because, you see, the numbers must have 3 digits. They must be 3-digit number. And this is not a 3-digit number. 0, 1, 3, say. 0, 1, 3. Because this is 13. It's a 2-digit number actually. So for the first place or the hundredths place, I cannot use 0. I can use any of the remaining 9 non-zero digits or non-zero numbers. So the number of choices for this place is actually 9. Now once this choice has been made, say I have chosen 1 in the hundredths place. Then for the tens place, what are the numbers or what are the digits remaining? I have 0, 2, 3, etc. up to 9. I am again having 9 choices. Now can I put 0 here? Yes, I can put, because now there is no fear of having 2-digit numbers. This 1 in the hundredths place already takes care of that fact. So now I can put 0, but since I have already chosen something for the hundredths place, say 1, so I am left with these things and I still have 9 choices. So the tens place can also be chosen in 9 ways. Now once one such choice has been made, say I have put 0 here, then the number of choices decreases. Now I have 8 choices. So in this case, the number is 9 times 9 times 8. So this many numbers are there between 100 and 1000 that have distinct digits. Okay, and what is it? I hope I am correct. 9 9 81. Yes, 600. There are 648 numbers in this set. So the cardinality of the set is 648. Hence, cardinality, if you recall, cardinality of a set, we chose to use this notation, is 648. It's not necessary to phrase this problem using set theory, but it does not hurt to do so, especially since we will have to carry this knowledge with us. Okay, whatever we learn, we have to at least remember these elementary things. So let's now move on to the next one. Now as we go further and further down this problem lane, soon we will see that these methods are not enough. We will have to devise something new. We will come across that soon. So let's now take this one, which has 2 subdivisions. In how many ways can the letters of the word daughter be arranged so that there are 2 extra conditions given, all the vowels are together. All the vowels are together. And B, all the vowels are not together. Okay, so now we have a word, again a word. Okay, here itself we will have to formulate, although we will be using counting principle, but in a slightly more complicated way than usual. So let us look at the first part of the problem. We have daughter, right? Now, Ghteer. Now here we have been asked to find those arrangements where the vowels are together. So let's just locate the vowels A, U and E. There are only 3 vowels. So before we try to use the counting principle, let us just see what we have been asked. The vowels must be together, right? So these are the possible arrangements. I mean, I'm not going to write all of them, there will be many. So I'll just write some 2 or 3 arrangements which are being asked here. So say I can write D, A, U, E. Okay. Ghtr. Here the vowels are together. Okay. Now this is one arrangement, this is another arrangement. UAE, United Arab Emirates. This is another arrangement which is different from this one. But this group of letters, which are the vowels, they can be anywhere. And also these consonants can arrange themselves in any way possible. Say I write GH, AEU. Now deciding to write a still different arrangement of the vowels themselves, GH, DTR. These are all possible arrangements. However, this word itself is not an arrangement that we need. Here all the vowels are not together, only two of them are together. All of them must be together. Those are the arrangements that we need. Okay. But how are we going to use the counting principle? That we have to understand. So for doing that, we have to see what is happening here in these examples. You see that things, actually what are we doing here? Instead of having how many letters are there, 1, 2, 3, 4, 5, 6, 7, 8, instead of dealing with 8 objects, actually we are dealing with 1, 2, 3, 4, 5, 6 objects. One of the objects is a composite object which consists of other objects. Okay, we are moving around these 6 objects. So do you get that point? We are actually moving this whole group together. Wherever we place the group, A, U and E must be together. That's the condition. So, and these 6 objects are distinct. D, H, G, T, R, these are all different. This object is also different from all of them. So, first of all, we have to arrange these 6 objects. And we already know, since these are 6 distinct objects, the number of arrangements is 6 factorial, right? The number of arrangements is 6 factorial. Do we have anything? No, we don't have any repetition, right? D, because these are distinct. Am I missing something, or is it right? D, A, U, G, H, T, yeah, it's right. So the number of arrangements is 6 factorial of what? Of arranging these 6 objects. But as you can see, in these arrangements, these 2 objects are not counted as different, because this object that I am putting here, in this counting, where we are counting 6 factorial objects, the internal permutations of these 3 letters have not been accounted for. That we have to account for separately. For each of these 6 factorial arrangements, the inner letters can among themselves be arranged in further 3 factorial ways, because they are 3 distinct objects. So the total number of permutations is 6 factorial times 3 factorial. Okay, this is also using counting principle, but in a slightly more complicated way, and that makes sure that the vowels are together, right? And then this is part A. In part B, we have been asked to find those where the vowels are not together. So this is an example. These are not examples. So from the total number of permutations, without any of these restrictions, If we subtract the number of permutations where the vowels are together, then that will give us the number of permutations where the vowels are not together. Now the total number of permutations, how many words were there? 8, I think. 1, 2, 3, 4, 5, 6, 7, 8. So since these are, how many letters are there? 8 letters. So these letters can be arranged without any restriction in 8 factorial ways because they are distinct. Minus, this is the number of permutations where the vowels are together. So this gives us the number of permutations where the vowels are not together. And this is the answer, right? Then in the next one, things are going to get even more complicated. So this is also a similar question. In how many ways can the letters of the word I don't have place. Letters of the word independence be arranged. Okay, so that is the first part of this question. Additionally, it also asks how many of them, okay, now there are some parts. Part A, how many of them start with P? B, have all the vowels together. Part C, don't have all the vowels together. And part D, start with I and end with P. Okay, so these questions. So let us start the solution by first of all counting the number of permutations of the letters of this word independence without any restriction. Independence. Independence. Yeah. So we go, this one is easy. Here, this is the situation of the example with which we started this video. Here, some of the letters are repeated. So first, let us count the number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in total, there are 12 letters. 12 factorial. Then we take care of the repetitions. I appears only once, N appears once, 2 times, 3 times. Okay, so 3 factorial. But there are more repetitions, right? D appears 2 times. Let me use a different symbol. D appears 2 times, so we multiply this by 2 factorial. E appears 4 times, 1, 2, 3, 4. So we divide by further by 4 factorial. P does not appear more than once. C also does not appear more than once, just like I. So this is the number of permutations of the letters of this word, right? So that is the first part of the question. Now then come the subdivisions or the parts, the other parts. How many of the letters start with P? So if you think of it, you have 12 places, right? 1, 2, 3, 4, etc. 11, 12 place. I'm not showing all the boxes since that does not serve any purpose. Now the restriction at here is that we want those arrangements which start with the letter P. So the first place is fixed for P. If it's reserved for P, it cannot be changed. For the remaining 11 places, we have now this is gone. This one is gone. For the remaining 11 places, we now have to find the number of possible arrangements. There is no other restriction, okay? The only restriction is that the arrangements should start with P. That we have taken care of here. Okay. So the remaining places, first of all, considering them as distinct objects, the number of arrangements is 11 factorial. But that's not actually the thing. We have to take care of the repetitions. Since P itself was not repeated in the actual word and P is appearing here, so here the number of repetitions even when P appears in the first place are the same. N appears 3 times, D appears twice, and E appears 4 times. So we have to divide by the same number. You can see that this number is significantly lower than this, smaller than this number. That's because adding a further restriction takes away many elements, namely those, takes away many arrangements, namely those arrangements which do not start with P. Now there are so many arrangements that do not start with P. So they have been taken out and we are left with this many arrangements where P is the first letter. Then comes part B. Again, have all the vowels together. So we have to proceed just like how we did in the previous problem, but here we have to be extra careful. So let us first of all note the vowels. I and the 4 E's. Okay, so they are the vowels. So let's just write them like this. Okay, so this is, in this case, this is our composite object. The remaining objects are, of course, N, D, P, then we again have N, D, N, C. Is it, have I written it correctly? N, okay, let me see the repetitions. N appears 3 times, D appears twice, P appears once, C appears once. So this is what happens when we take the vowels together and write the remaining consonants. Now here also the procedure is same. Now we look at these objects, although in this case you see these are not distinct. It's unlike the previous example where the letters of the word daughter, they were all distinct, but in this case there are so many repetitions. In the composite object also we have repetition of letters, outside also we have repetition of letters. Anyway, so the number of objects in the present scenario is 1, 2, 3, 4, 5, 6, 7, 8. So they can be arranged in 8 factorial ways. But these objects are not distinct. This does not appear more than once, that is okay. The composite object appears only once. But in the remaining portion, we have n again appearing 3 times, 1, 2, 3. So we divide by 3 factorial times, but there are more repetitions. D appears twice. So we divide by 2 factorial. P and C do not appear more than once. Okay. But that is only the number of arrangements of the objects like this. We have not taken care of the internal arrangements. Now inside, for each of these arrangements, inside we can rearrange this. Now here the number of objects that we can see is 1, 2, 3, 4, 5. 5 factorial. But here also we have repetitions. How many? 4 is. So we divide by 4 factorial. So this is the number of ways of arranging these letters of the word independence in which the vowels are together. Okay, so this number. Then we have part C. Part C, we now know how to write this down. From the total number of arrangements where we don't have any restriction, we have to subtract this. So this number is 12 factorial divided by this 4 factorial minus this one. 8 factorial divided by 3 factorial times 2 factorial